Hey AP Chemsters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. Today we're doing 15.9 polyprotic acids. But before I really begin, let me remind everyone that you should be having a calculator with you, you should be following along, you should write down questions if something doesn't seem right to you. I do make mistakes, you know. And just be an active participant in this. So calculate when I calculate. When I pause this, you pause, you finish out the problem, and that will help you a lot. So let's begin this section. So 15.9 is the polyprotic acids. Poly meaning many, protic, protons. Protons we said was an H plus, so we're saying many H plus acids, or acids that can donate more than one H plus is really what it's saying. So when you do this, it's a stepwise dissociation. We kind of alluded to that earlier where we said like how many H's will be lost with carbonic acid, one at a time. And that's what we mean by stepwise dissociation. So in the case of sulfurous acid, the question then becomes, all right, well, how do you break down the sulfurous acid? And the answer is one at a time. So let's look at these Kas, okay? Let's look at these if you would. Ready? Okay, so there's sulfurous acid, and we see that the Ka for number one, for the first one, is 1.5 times 10 to the negative 2. And I got that right over here. Okay, I think Jonathan was looking at it too. And then over here, what about the second one? So this little 2 right there. Well, what about the second dissociation? Well, it looks like 1.0 times 10 to the negative 7. And really, what does that mean to you? This is a factor of 10 to the 5th difference. We're talking about 100 million times different, I'm sorry, 100,000 times different in the ability to dissociate. So that is a huge jump, really, from 10 to the negative 2 to 10 to the negative 7. And so what does that mean? This is going to be the main contributor of the H plus ions, but this still will break up too, all right? So let's look at sulfuric acid, the strong polyprotic acid. Sulfuric acid is very unusual in several ways. First of all, as you, I sure hope, know that sulfuric acid is a strong acid. And so we have the Ka, it says over here, it's large. You really can't express it, it's infinity. But look at its Ka2. That value is 1.2 times 10 to the negative second. Oh my goodness, that is a very large K value. Even for most acids, their first value is not that large. So you could say that this bisulfite ion is a very strong weak acid, okay? Kind of on the order of, let's say, hydrofluoric acid. That's another very strong weak acid. So it says right here, sulfuric acid dissociates to a greater extent, even in its second step, than weak acids do in their first step. And the second step, oh, check this out, underline this, cannot be ignored in the calculation of the pH for dilute solutions. Okay, so guess what? I bet we're going to be doing one of those. You're right. So it says finding the pH of a polyprotic acid solution. Usually, the amount of the hydronium ion is formed by the first step is much, much, much larger than formed in the second or third step. You got to look at those Ka values to really know that. And Le Chatelier comes back in play again. So how would the formation of the H3O plus ion in the first step affect the formation of the H3O ion in the second? And we're going to answer that as we work through the problem. So I'm not going to answer that now, but we'll discover that later. So let's go ahead and do problem 46. So problem 46 says, calculate the pH of a 0.0100 molar sulfuric acid solution. So here is your first step. Your first step is the dissociation of sulfuric acid, which is a strong acid. Notice I have an arrow here. Okay, a single arrow, strong acid. So what does it mean to be a strong acid? It will 100% of the time completely dissociate. All right, the K value is large. It's infinite in a sense that because our setup, we're going to have 0 in the denominator. We're going to have Q equals a number divided by 0. That's infinite. So K is a huge, huge number. So let's check this out. So if we start off with a 0.01 molar solution, it breaks up. So it has a 0.01 molar of H3O plus and a 0.01 molar of the bisulfite ion. Excuse me, bisulfate ion. So what's going to happen next? What will this do in solution? Well, it's going to act like an acid as well. So it's going to start off here, and it's going to have your bisulfate ion, and you're going to add it to water, and it will also donate its H plus to the water to make hydronium and the sulfate ion. Now, what is different? Oh, I'm sorry, by the way, I did want to show you this. Okay, I looked that up. What is different about this problem is that the initial concentration of the bisulfate ion is indeed 0.001. See how that went from here to there? Here, let me kind of draw that. Yeah, we went from this number here, right? So however much I started off from the dissociation of my strong acid, that's how much of the bisulfate I'm going to end up. But what is different? Look at what I initially have in my beaker. So I already have an initial amount of the hydronium ion. Oh my goodness, what is that going to do? Well, my math is going to be a little bit different, so beware. But notice, I still have 0 of the sulfate ion. So Q is still going to be 0, so it's still going to shift to the right. Okay, and so what is going to be my equilibrium expression? You go ahead and do that. Is this what you got? What's different? Oh, this is what's different. So when I set up my K value, my equation's gonna be a little bit different. So let's see what happens. All right, so go ahead and set up your Ka value, products over reactants. Go ahead and write that out. Hopefully that's what you got right here. Sorry to switch that out. So you got your sulfate ion, your H3O plus ion, and your bisulfate ion in the denominator. So let's plug in some of these numbers here. You'll see that here is my X. I guess I reverse them. The X is your sulfate ion, and the 0.0100 plus X is your hydronium ion, divided by the 0.0100 minus X. Now look what this is equal to. Oh my goodness, this is a bummer, isn't it? That's why I have a sad face. Ich bin sehr nicht fröhlich. Ich bin sehr traurig. And for these folks that don't take Germans, I am not happy. I'm very sad. Why am I very sad? I cannot use the approximation that X is very small when the Ka value is so big. I actually have to use the quadratic equation. Oh my. So when you do that, here I worked it out as far as it goes here. I multiplied both sides by the denominator, and I distributed the X over here. And I'm going to work over here on the left-hand side. And when you combine like terms, go ahead and pause this and you combine like terms. Okay, did you get this? And now we need to solve for X. So pause this, use your calculators, figure out what X is. Hopefully you got this value right there. So I'm not done yet. What is X? X is the amount of the sulfate ion, and X is the amount that you're going to add to the hydronium ion. So you're going to take the 0.101 or 00 from the first dissociation, the first step, and then you're going to add the new value, the X that you just solved for. That's this X here. And this is now the concentration of the hydrogen ions. What are they asking you for? They want the pH. So what do you think you need to do next? Take the negative log of 0.0145 molar, and there you go. pH is 1.84. I hope you got that. And you'll notice that this is a significant contribution to that number. All right, let's do the next one. We're going to learn a little bit about vitamin C. So it says find the pH of a 0.100 ascorbic acid vitamin C solution. All right, so here is vitamin C. It's an acid. So what do acids do in water? It makes H3O plus and this ion next. And I looked up the K1 value for you, and it is 8 times 10 to the negative fifths. And so I'm going to go off you a little bit there, okay? I think that might be kind of helpful. So here's my initial setup, and notice that Q is 0, so it's going to shift to the right. And so there's my shifting to the right. And oops, I forgot my little line. Let me find my little line. And so there we go. So this is my value here. And as always, what do I need to do? I need to set up my Ka value. Don't be lazy. Write it all out. So H3O plus the ascorbate ion. And then here's my ascorbic acid. So now plug in your values, x squared over 0.100. Guess what that's equal to? 8 times 10 to the negative fifth. Go ahead and pause this and solve for x. Oh, wait a minute. Is your approximation going to work? I think it will. So you can actually, I forgot about that. You can actually go ahead and like, oh, yay, happy day. Okay, and now go ahead and solve for x. Okay, what did you find out that x is equal to? I got x is equal to 2.8 times 10 to the negative 6. Now, what is x? Keep in mind, what is x equal to? X is equal to the hydrogen ion concentration, right? Isn't that what x is equal to? And now they want to know what the pH is. Well, just plug that in, and there we go. Now, are you saying, Mrs. Vanderlooy, have you forgotten something? What about this ion? All right, why didn't you count the H3O plus from the second dissociation? Well, I looked at the chart on the earlier page, and I found what the K2 value is. So we're going to need the K2 value for problem number 48. So I just thought I would throw that there now. And look what happens when you put that ascorbic acid, or excuse me, ascorbate ion into solution. What happens then? Well, I get H3O plus and I get the ascorbate ion. And what's going to happen? Look at that K value. 1.2 times 10 to the negative 12. Holy cow, look at the difference between negative fifth and negative 12. We learned earlier from when we were talking about the weak acid combined with a weak acid combined with a strong acid. I forget what section is it, 15.7 maybe, where we said if the K values is at least 10 to the negative fifth difference, we really can ignore it. You can go through and do the second dissociation, but because the K2 value is so much smaller than the K1 value, that really whatever is dissociated from the H3O plus then is so insignificant, why bother? Okay, so what would happen if the K2 was maybe like, oh, 10 to the negative 7th, 10 to the negative 8th? You probably would have to go ahead and do that second dissociation, but because this value is so much bigger, you really don't. Okay, so here's this problem now. Goodbye, Jonathan. And we can go ahead and plug in the values. Now, wait a minute, what is our initial values? Well, where do they come from? I bet they come from up here. Here is my initial value. Okay, that's my initial H3O plus. That's my initial the hydrogen ascorbate ion. Yeah. So we can go ahead and use those same values again. Okay. Here's the same value we solved for before. Here's my X. Here's my H3O plus, but I don't have any of this ascorbate ion left. Okay. So what happens? Q is still 0. It's still going to shift to the right. And so here is my setup. Okay. All right, here's my Ka value. Notice it's H3O plus the ascorbate ion over the hydrogen ascorbate ion. And I can plug my values in. But look what happens this time. I don't know why x squared is there. All right, look what happens this time. Can we use that approximation? Yes or no? What do you think? Yes, we can. Look at this value. It's really small. So does that mean I can cancel out these numbers? Yes, I can. I can't cancel out this one. Only the ones that are multiplied, or excuse me, that's wrong. Oh, excuse me. Only the ones that are add or subtracted you can cancel out, not the ones that you multiply. But now what? Oh my goodness, your life is so easier. I don't even need a calculator for this problem because now this number cancels out this number. And so what is it that x is equal? Did you notice what x is equal to? It's equal to the value of the K2. And so what else is this equal to? This is equal to the ascorbate ion. And isn't that what they asked for? Yeah, it is. Now, why did they ask us for the pH value? Has it changed much? If you took this number right here, look at it, 1.2 times 10 to the negative 12, and added that to 2.8 times 10 to the negative 5th, is that going to change your hydrogen ion concentration by that much? No. Okay, so why they ask for pH? It's the same as before. I believe it is 2.55 from the problem number 1. So it hasn't really changed the hydrogen ion concentration, but we are able to find the ascorbate ion concentration. It's really pretty darn small, isn't it? Okay, and then I wrote, notice anything? What did we notice? That the concentration of the second dissociation ion, so for a diprotic acid, a weak diprotic acid, is equal to what? I think you're going to notice it's equal to the Ka2 value. All right, so notice that the ion concentration is equal to the Ka2 value. That makes it pretty handy, doesn't it? So now we have this general result applies to all diprotic acids where the X is small, approximation works. So really we're looking for Ka values of -5 or smaller. And so here you can see kind of a picture in your notes. I don't know why this isn't showing up too well. I can maybe do that. And so here we can say, using ascorbic acid, that here's my hydrogen ion concentration from the first association. Here is my hydrogen ion concentration from my second one, pretty small. And notice that it really hasn't changed much, all right? That -12 doesn't change a whole lot. So there you go. Let's see what's the next page. All right, so we are calculating today the pH of a 5 molar phosphoric acid solution and the equilibrium concentrations of H3O plus, or excuse me, H3O or phosphoric acid, I can get it, the dihydrogen sulfate, the hydrogen phosphate, and the phosphate ion. I hope I said that right. So here's the first step dissociation of phosphoric acid, which is a weak acid, 10 to the negative 3. It's not that weak. It's a fairly strong one. And let's see what I do here. All right. And I know that it's 0, so I know it's going to shift to the right. And here's my equilibrium. And this is where I got kind of lazy. All right, I said x squared over 5 minus x is equal to 7.5 times 10 to the 3. I combined like terms. I had to use the quadratic equation, and I came up with x is equal to 0.19. If you want to pause this and check my work, make sure you get the same thing I do, please go right ahead. So you can just pause now and then catch up with me when you unpause it. So x is 0.19. It is the dihydrogen phosphate ion, and it's equal to H3O plus. So if I look at the next step, okay, so if I look at the second step dissociation, I'm starting off with this. And here is the K2. Now this makes me a lot happier. Look at that, -8. So my math is going to get a lot easier. But what is my initial concentration? What's my concentration of the dihydrogen phosphate? Oh, it's 0.19. What's my concentration, my initial concentration of H3O plus? It is 0.19. Oh, okay, so then I'm going to do this. And when I'm all done, there I go. Now, watch what happens when you set this up. This is kind of exciting, isn't it? So 6.2, actually I'm going to do the work for this one. 6.2 times 8 is equal to products over reactants. And once again, just like before, because this is such a small number, we can get rid of the x's that you are adding or subtracting to. Don't get rid of this x. You need to keep that one. But what else is so exciting? Hey, look at this. These guys cancel out. And so what does x end up equaling is that same Ka2 value. Isn't that just like the last problem that we did with ascorbic acid, that the second diprotic, stepwise, that this second ion here is equal to the Ka2 value? Yes, it is. So it's still consistent. That's awesome. And now what? We want to see what the third step is. So now we're going to take this hydrogen phosphate ion, And we are going to also hydrolyze it, add it to water, and now we're going to get the phosphate ion. And look at this K3 value, 4.8 times 10 to the negative 3. And that's super duper small, and see what happens to our values. But first we need to set up our ice table as always. Oh, sorry, I jumped the gun here. And oh, look at these values here, just a little bit different. See this value from above before? I put that over here. That's this value. But where did 0.19 come from? That's not this number. Well, when I added this number to 0.19, it is super duper small. So it really did not affect the change of the hydrogen ion concentration. So it is still the same value as I got up here. See that? When you add such a small itty bitty number to it, it's not going to really change the molarity of the hydronium concentration. All right, and so put it all together. Here we go. And so what is the math for this problem going to be? Well, same as before, sort of. Here's my Ka for the third step. It's equal to the 0.19 plus x times x over 6.2 times 10 to the negative 8 minus x. But just like before, I bet x is going to be so small, it's not going to make a whole lot of difference to that value. And so now what I have to do is take these two terms. What I did is I put 0.19 divided by 6.2 times negative 8. You got a pretty big number. Then I took this number divided by this quotient here to solve for x. And here it is. I told you it's going to be a small number, 10 to the negative 19th. I can't imagine how small that number must really be. Oh, there we go. And so that is my phosphate concentration. This is my hydrogen phosphate concentration. Here is my dihydrogen concentration, dihydrogen phosphate concentration. Here's my H3O plus concentration. And here is my H3O or H3PO4 concentration. So the only thing out of all this is lacking. I still need to find what pH is. So for all intents purposes, I need to go right back up here again. And what was H3O plus 0.19? Anything added to it from the other steps are going to be so small that with two sig figs, it really doesn't make a whole lot of difference. So 0.19, took the negative log of 0.19, and I got the pH of 0.72. So yeah, it is a fairly acidic solution, isn't it? Because this is a fairly strong weak acid, and 5 molar is really strong too. So yeah, it's a really acidic problem, or acidic solution, and there we go. So that's a pretty complicated one, and if you really understand what exactly went on here, you're doing great. So hopefully this helped. See you later. Bye bye.